So hello again. This is Roger Kochbar for the Bioelectricity course. We're in week 7 talking about extracellular voltages and potentials and recordings and other interesting ideas. And this is lecture segment number 9. When one talks about extracellular potentials, at first this subject seems so simple. It's just some recordings. Or on the other hand, it's just a couple of sources and sinks spreading out their currents throughout the available conducting volume. On the other hand, it rapidly becomes very confusing because things that are similar but not the same get all mixed up with one another. That is to say, recordings of voltage versus time, recordings of voltage versus distance, sources as determined from transmembrane voltage, sources as determined from membrane currents. It's helpful to keep looking at things from several different points of view so as to put them together in a useful fashion. So in this segment, I'm going to show a series of cartoons. Now it's important to keep in mind these are just cartoons, which I drew for the purpose of illustration. On the other hand, some of the basic ideas are illustrated perhaps more clearly by looking at things this way. So in this cartoon, we have at the bottom a fiber. In our fiber, there's an action potential. The action potential is located in this region. And in our fiber, the action potential has one source and one sink. Here is the source, place where current is coming out of the fiber. I'll put a plus mark over it. Here is the sink, the place where current is going in. Now, of course, this cartoon is incorrect because it simplifies things and draws all the current coming out as if it's coming out on a single line. That's not so because it's spread out over a little distance. Similarly, the sink is a single line. That's not so either because it's spread out over a little distance. But it is true in the real case that the source and sink exist over an amazingly short distance compared to the radius of the fiber, and a very, very short distance, oftentimes comparing to the dimensions of the person or the animal or the tissue from which the recording is being made. So it is. The spirit of it is true, even though the detail is false. So with that source and sink, let's see what happens. Current comes out. It makes use of all available pathways to go between the source and sink. So some just comes directly over. But other current makes a longer loop, like that. And still other current makes a very long loop, out here on this big loop. In a general way, the current will minimize the energy used, so less current will flow on the longer pathways. On the other hand, you don't want too much current flowing on any pathway, or the voltages it would create would grow so large that they would push current away. Or you could say when all of that is in balance, that's the pathway set that you have. We notice on our slide one other detail. The intracellular current, this current, is moving to the right. That means this is the point, approximately, that's halfway up the upstroke. This area is the part of the tissue that is becoming depolarized. This is the part where the action potential is at its peak. But everything is moving down the fiber here to the right. In the previous cartoon, we were talking only about the excitation and current flow. Here we introduce some electrodes that are outside of this fiber to see what voltages one would measure there. So here the cartoon is picturing a situation where you have a voltmeter. The positive lead is going over here to A, and the negative lead is going over here to B. This is actually a pretty common recording setup. One lead, the A lead, is thought of as the probe and is brought down very close to the fiber or to the active tissue. The other lead, the B lead, is thought of as the reference, and it's backed off quite a distance. Here on the cartoon, I've shown them more close together than they usually are in a practical situation. In any event, we see that the current is flowing from A to B. That's the pathway. The medium is resistive. Therefore, there's a voltage from A to B, and that voltage is positive. So we're right up here on our curve. Now at the next moment in our cartoon, excitation has moved over to the right. Our electrodes are now, at this moment, right in the midpoint of the pattern. Current is flowing from right to left. There is no current that's flowing from A to B or B to A. Consequently, the current is not generating any voltage in between A and B or B and A. And if we look over on our recording, the voltage between A and B has gone back to zero. Now we're here at a third moment in our excitation sequence. The action potential has moved on down the fiber to the right. The current loop is still a very large current loop, but the electrodes are in a different position in the loop. The current loop is still big, but now our electrodes, for our electrodes, current is in the direction from B to A. That is to say, the voltage from A to B will be negative. So as a consequence, over here on our trace of voltage versus time, we see a waveform that is negative at that moment. Now there's no cartoon that follows up, but obviously what's going to happen next is that this excitation is going to go right on off the end of the fiber. Or putting that a little bit more accurately, excitation will come to an end as it approaches the end of the fiber. So the consequence will be that the voltage will rise and go back to the baseline, so we'll have this segment where excitation has ended. I hope you enjoyed those cartoons. They're interesting to look at. Sort of fun to look at it that way. Drawing cartoons is an interesting instrument that we use to perfect our understanding. And here this guy, who lives on the Duke Union building, is using an instrument for his enjoyment. Thank you for watching. We'll see you in the next segment.